Let's take a look at example 9. We want to find the volume of the solid described as follows. The base of the solid is the region enclosed by this parabola and the x-axis. Cross sections that are perpendicular to the y-axis are squares. I don't know about you, but when I see a description like this, I can't really visualize what's going on. So let's take a look at this. We'll use a three-dimensional graphing software to visualize this a little bit better, and then we'll solve the problem. Once again, our first step is to draw the two-dimensional base of this solid. So this is using the parabola y equals 4 minus 3x squared. And if we sketch that, it looks something like this. This is the base of the figure. This is y equals 4 minus 3x squared. Now, how is this figure defined? Well, this is the base. We need to somehow construct a three-dimensional figure from it. And the problem statement says that the cross sections that are perpendicular to the y-axis are squares. What does this mean? Well, let's think of taking a cross-section perpendicular to the y-axis. Imagine that we're viewing this three-dimensional solid from directly above. So this is only the outline of the solid. There's really some solid shape here that we can't really see because we just see the silhouette or the outline. But the cross-sections that are perpendicular to the y-axis are squares. So here's a cross-section just looking at it from above. But now if we think of sort of tilting the view angle, this cross-section would be a square. I'm trying to draw a little bit in 3 dimensions here so we can sort of see what this would look like. That would be a cross-section of this shape. Now, once again, this is really difficult to view just in 2 dimensions. So let's go ahead and look at a 3-dimensional graphing visualization. So here we have the parabola 4 minus 3x squared. And we're imagining taking cross-sections perpendicular to the y-axis that are squares. So here's what those cross sections look like. I'll shift this around in 3 dimensions a little bit. The cross sections look something like this. And as we move these cross sections throughout the region, they are forming the solid. So if we can imagine moving these cross sections through the entire region, take them all together. These are really the slices, the representative slices that will add up. And as these move through the entire region, they describe the entire solid. So the full solid looks like this. It's this sort of beak-shaped solid. The base is the parabola, and the cross sections perpendicular to the y-axis are these squares. So now that we have a better idea of what this solid actually looks like, let's try to determine the volume. Here we have a representative slice of the volume. We want to imagine that this has some little bit of thickness, and let's call the thickness here, well, it's some change in y. I think I want to set up an integral with respect to y. So let's call the thickness dy. And if I can find an expression for the volume of this slice, then I can integrate in terms of y. So I'll integrate from 0 to this height of 4. I can integrate to find the total volume. So my main goal here is to find an expression for the volume of this representative slice. Now, what are the dimensions of this slice? Well, we know that it's a square. And what is this length here? Well, the way I want to think of this is that half of the length is some x value. Let's just call this x. So that's each side of the y-axis. So really this length is 2x, and it's a square. So this is 2x, and this length here is also 2x. So I have 2x by 2x square. But I want to integrate in terms of y. So what I need to do is use the expression for the parabola to solve for x and get x written in terms of y. So let's do that now. We take the y equals 4 minus 3x squared, and we want to solve for x. So 3x squared equals 4 minus y. If I rearrange a little bit, divide both sides by 3, and take the square root, I have x equals the square root of 4 minus y divided by 3. All right, now back to this picture here of the slice. It's a slice. It's actually a rectangular solid that has dimensions 2x by 2x, and then the thickness is dy. So the volume of this slice is 2x times 2x, so 2x squared dy. But now instead of using x, we want to use the square root of 4 minus y over 3. So we will write this as 2 times the square root 4 minus y over 3, quantity squared dy. Well, this simplifies a little bit. I'm squaring a square root. So those go away. I'm also squaring the 2. That becomes a 4. So I have 4 times 4 minus y divided by 3 dy. That is an expression for the volume of this representative slice of the three-dimensional solid. Once we've got this, we've really done the majority of the work. In order to find the total volume, I just need to add up all these representative volumes by using an integral. I'm integrating with respect to y. So I start from a y value of 0, and I add up volume until I get to the total height of this figure. That's a y value of 4. If we plug in x equals 0 here, we get y equals 4. That's this y value here. So the total volume is the integral from 0 to 4 of all these representative volumes. 4 times 4 minus y over 3 dy. We won't take the time to actually evaluate this integral, but it's actually quite a simple integral. 4/3 is a constant. We could take that out front. And we're really just integrating 4 minus y. It's a fairly simple polynomial. We could find antiderivatives, plug in the limits, and get the volume of this fairly easily. Finally, let's work through example 10. Example 10 is actually fairly similar to example 9. We have the same parabola, and we have the same base of the region, but now cross-sections that are perpendicular to the x-axis we take to be squares. That's the only difference here. We will get a different looking shape, and we'll visualize this, but actually problem 10 is a little bit simpler than problem 9 because we can integrate in terms of x, and we don't have to solve for this function in terms of x. Let's take a look. So once again, we draw the base of the region. It's this parabola again, 4 minus 3x squared. And let's think of taking a representative slice here. Well, a representative slice is now perpendicular to the x-axis. So it would look something like this. Perpendicular to the x-axis, here's a slice, and we take this to be a square. So if we can sort of visualize this in 3 dimensions, it looks something like this. We have some little bit of thickness here, which is a distance along the x-axis. So we'll call this thickness here dx, and the height is simply the y value of the function. So this side length we could call y, and it's a square, so it's a y by y square. We have a rectangular solid. So the volume of this slice is just y squared times dx. But now y is 4 minus 3x squared. So we can express this all in terms of x. 4 minus 3x squared squared dx. We obtain the entire solid by moving these squares from this starting x value to this one. We have to solve for those limits of integration. But before we do that, let's make sure that we understand visually what this looks like by looking again at the 3D software. So here once again we have the parabola, and now we take cross sections perpendicular to the x-axis to be squares. So this is the base, and the cross sections now look like this. That's a square perpendicular to the x-axis, and if we take all these cross sections, all these slices, they will describe the entire three-dimensional region. So there's all the different slices, and when we take them all together, the 3D solid looks like this. Notice that it's a different solid than what we had the last time. The other solid was like a beak-shaped figure, and this is a completely different looking solid. So now that we know what this solid looks like, let's solve the problem the rest of the way. There's only one more piece of information that we need. We need to know what are the x values of these limits of integration. And in order to find these, we want to know when y equals 0. So we will set the y function equal to 0 and solve for x. 4 minus 3x squared equal to 0. We have 4 equals 3x squared. X squared equals 4/3. this tells us that x equals plus and minus the square root of 4/3. So our a value is negative square root of 4/3. B is positive square root of 4/3. Those are the limits of integration. I have an expression for the volume of a representative slice. I have limits of integration. I can now set up the total volume integral. So the total volume here is the integral from negative square root of 4/3 to positive square root of 4/3, and we are integrating the representative expression, 4 minus 3x squared dx. And that is the volume of this solid.